I'm going to talk about how to approximate a binomial distribution using a normal distribution. So first I'm going to introduce the key. Whenever you see a blue X, that's referring to an individual point on the x-axis on any of these graphs or plots. Whenever you see just an X with a line over it, that's the mean or the average in a data set, or usually the center of what's going on here in the plots with the normal distribution and with the binomial distribution. That's what the major part of the curve centers around. Whenever you see a green lowercase sigma, that is the standard deviation. That is calculated for the normal distribution at least by taking each data point, subtracting the average from it, and then taking that and squaring it, and then adding it to the next point under the same guidelines I just said, which was to subtract the average and square it. When you do that for all the data points and then you divide by n, and then you take the square root of the whole thing that I just said, that gives you the standard deviation. For p in parentheses, and when you see a value in parentheses, that's usually an x range, a range of x values. And then you probably see a subscript, which you'll see down here. You'll see the probability for normal distribution of that range, and you'll see the probability for binomial distribution for that range to make a comparison. That means probability of whatever that event is, and that event could be any one of a number of actual events in a range. For example, when you see z, that is the z value that's used to actually determine the probability in the normal distribution. That's the number of standard deviations from the average that a point is. So I'm going to review that here in a little bit, but when you see the number n, purple n, that means number of trials or number of data points in a set. When you see a lowercase b, that is the continuity corrector, and that is helpful in approximating the binomial distribution, and I use 0.5 like Deborah Rumsey does in the book Probability for Dummies, and that does help make it a little bit more accurate, especially for lower values of n. So I'm going to review the normal distribution with you. Each of these dotted lines that you see going up here, those all represent intervals that are one standard deviation in length. This is the mean, the average. The whole curve is centered around it. When you go just one standard deviation this direction, and then you take the area between this standard deviation and that standard deviation on either side, you get about 68% of the curve. That's most of the curve within the first standard deviation. When you go to the second standard deviation, it's another 13.5% on either side. So you end up with about 95% of the data being within those two standard deviations on either side. When you look at three standard deviations on either side, you're looking at 99.7% of the data. And if you just look at one side, how much is the probability of it being beyond that on just one side? That's only 0.15% or 0.0015. So this is very well centered in the middle for the normal distribution. A lot of things abide by this rule in general, or approximately by it. I'm going to talk a little bit about how to take a binomial distribution and just use this to figure it out approximately. It's not a perfect calculation, but it certainly is worth the time because of the actual nature of the formula for the binomial distribution, which I'm going to talk about now. So I'm reviewing this, but to calculate a binomial distribution for a certain number of trials and number of successes, you want to know the probability of having a certain exact number of successes. Well, you have to look at it sort of like what we looked at with the combination problems. So let's say you have coins, you have 5 coins, and you flip them. They can either be a head or a tail, right? Well, let's let's say you want to find the probability of it being 2 heads, right? Notice that the first 2 don't have to be heads for that still to be true, right? Well, how many different ways can we have 2 heads when there's 5 flips, right? Well, there are you want to find all the combinations basically, and they're the same probability, which is why the condition for the binomial distribution means that each outcome has to have the same probability. So it's 1/2 to actually have 1, and then it's another half to have the other one. If you're just flipping a coin twice, then there's only a 1 in 4 chance of you getting 2 heads, right? Well, this part here is saying you take the probability of getting a success and you raise it to the power. When you do that, that's the same thing as doing it twice in a row. So that's why I'm showing you twice in a row here. This part here is taking the number of total trials, subtracting the number of successes. When you do that, that's 3, because that's 5 minus 2, which is 3. And you're raising 1 minus the probability of getting a success, which is all the other probability. In this case, that's just 0.5 again. And you're taking that, you're raising it to the 3rd power, because there are 3 of them here. So if you look at this, if you take this part away and you only look at the part on the right hand side, you're looking at the probability of doing this, getting 2 heads and then getting 2 tails. That's what you're looking at. With dice, you're looking at the probability of getting anything but whatever you're looking for the rest of them, and getting exactly what you're looking for the number that you're using for x here on this. So that's helpful, that's great if you want to find one situation, but what about when you have like a head here and a head there, or in any other order, right? How many different ways can you do this? Can you have 2 out of 5? Well, that's what a combination is. So when you take n, choose x, shown here, to find the number of combinations, you're taking the number of trials, you're dividing by the number of trials minus the number of successes, and you're using factorial here, which means you take the highest number and then you multiply times the second, it minus 1, and then minus 2, minus 3. You keep going, you're multiplying. And you're also doing that up here with n factorial. And then you're also doing that with the actual number of successes. And that gives you all the combinations. So then, once we've done that, and we multiplied times what we did, what we figured out was the number of different ways to do this times the probability of each outcome, which are all the same, because it's just as equal to get these 2 as having this one and that one, whatever the case. That's why the binomial distribution works, and it's an exact calculation. What I want to tell you about is an approximate calculation for this. So let's take a look at some of the binomial plots real quick. So when you do a binomial plot for for flipping a coin 10 times, you end up with a very symmetrical plot. So that means that on this side, the probability of rolling no heads, or flipping no heads, is the same thing as flipping all heads. And if you look at it, they're the same. The red here is the normal distribution curve. If we were to put this into a normal distribution, the red is almost the same, but not quite the same. Because then under the normal distribution, if you go all the way this direction till infinity, there's only 0.15% here. But there still are some other outcomes that are well beyond this and well beyond the 10 here, if you look at it. So it's not going to be exactly correct. It's going to have different values for different things. Plus, there are slots in the middle, like in between each point. With the binomial distribution, all x is an integer. They're all integers. So you only can have 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10. You can't have 1.5 or 2.5 in here. So the plots are slightly different, and it's not going to be exact, but it is pretty darn close. And that's with 10 coin tosses. I'm using 30 rolls of the die in this example, and in this example it's not 50-50. It's 1/6 of getting a success and 5/6 of not getting a success. If you're just looking for one outcome, like you're rolling a 6, and you're rolling it a certain number of times, which would be 30 in this case, and you have a certain number of successes of rolling a 6 that you're looking for, especially when you're trying to find a range. What about, like, in the example we're going to go through here is how to roll 8 or fewer 6s. What is the probability? And if you were to subtract 1, or that 1 minus what we'd be finding, you'd be finding the probability of rolling 8 or 9 or more 6s all the way up to 30, which isn't very much probability. I use 30 here and 10 here because these are the minimum requirements under a binomial approximation. So the conditions of using this are you find the average first. Is the average greater than or equal to 5? Then you find the probability of not getting the actual outcome you want once, and take it times the number. If that's greater than 5 also, then it qualifies. So what you find here is as an event becomes more improbable or more probable, below or above 50%, that you have to have a higher n, because this starts getting skewed. And even in this case, you notice that these points on either side are not exactly symmetrical, whereas they are all symmetrical here. And that's why, because it's not going to look exactly like this, and it's also not distributed in the same position. Here you have symmetry. So you have the actual curve here in the middle. Here it's 1/6 the way away from the beginning, and then the other 5/6 are so improbable that you hardly have a curve there. You don't have a curve really there, the whole other 5/6 of the way. So that makes the calculation different than with the normal distribution. But the normal distribution is a good approximation, and it's good to use because you have to do all this math here. And in fact, even in Excel, if you try to go up to 171, I think it was 171 factorial, it doesn't let you do it. It just says num, because it doesn't know what that is. It can't calculate it. So you can only go up a certain number of trials using the exact calculation. That's why it's so useful to go with the normal distribution for this. So these conditions are what you have to check first. And as you get further away from 50-50 chance, it becomes more skewed, like I explained. When you take these values, you take the number times the probability. If it's low, that's a low number. That's lower and it's harder to meet, so you have to have more n. The same is true on the other side. If it's probable, if it's more probable than 0.5, you still have to find the lower probability, the probability of failure, and it still has to be greater than 5. Why is this important? Because the standard deviation for this is this formula here. It's an approximation of the standard deviation of what it would be for a binomial if you're looking at it like the normal distribution. So when you take the number of trials, take it times p and times 1 minus p here. With the coin, you get 0.25 for this part here, because you're taking 0.5 times 0.5. They're both 0.5. So you get 0.25, you take it times 10, that's 2.5. Then you take the square root of that, that's 1.58. So that would be that's the standard deviation, is 1.58 there. When you take and you calculate what it is for 30 rolls, which I picked, this isn't making a direct comparison because I used 30 instead of 10. I had to use 30 because that's the minimum you have to do to meet this criteria here. You end up with 2.04 as a standard deviation. So, moving along here, we talked about the coin. We talked about the fact that this is asymmetrical and it's not really the same as a normal curve. In fact, the normal distribution keeps going past 0 and past 30. Notice this only goes to 13, and that this is way over on the left side. If we were doing 5/6 instead of 1/6 for the probability, this is actually a mirror image. So this part that tapers off more is actually on this side. So it tapers up slowly, and then it drops down faster, and it's way over 5/6 of the way on the plot. So that's what a binomial distribution looks like when you plot it. And you have to do this equation each time for each one of these values. If you're trying to find a range of values, like the probability of rolling up to 8, then you have to do 8 of them, unless you're going to find the other, 22 of them, and then subtract, which would be a lot of work too. So either way you look at it, it's a lot of work to do a binomial distribution, because you got to do all that multiplication and division, and you only divide once, but you got to multiply a bunch of times on something, and that gets to be lots of work. Whereas this is easier if you can just find a z value and get it done. So this equation was for how to find the z value. It's the individual x value minus the average divided by the standard deviation, and that gives you your z value. Remember, to get the probability, you can use the z value to do that. It's either negative or it's either minus or positive, your z value, and you can look at a table which will tell you where it is probability wise, left to right here, or at least after adding all the area, it tells you what it would be. That z value again represents the number of standard deviations from the middle that you are, that point would be. So in here, it's kind of like saying if the average is 5, which it is, because 5 is 1/6 of 30. It's like, so one standard deviation would be to about 3. So if you get 3 6s in a row with the dice or not in a row, if you're rolling 30 times and you get 3 of them, that is one standard deviation away from the middle. But remember, that's only 34% less than the average, right? That's only 34% probability difference. And this is kind of cool, because now you can actually figure out how likely or unlikely an event is, if you know that and you just use this, if it's a good approximation. And these are the conditions for being a good approximation. So to figure out what the probability is of rolling a 1, 0, 1, 2, 3, 4, 5, 6, 7, 8 of 6s, we can use this, and that's what we're going to do. So what's the probability of rolling less than or equal to 8 6s? So first so I formalize this. I put this as P for the normal distribution, less than or equal to 8, x equals 8. Now, I'm sorry, I have to talk about the continuity factor first. So when you look at what a normal distribution would look like, that's the red here that I have near the curve. You notice it doesn't line up perfectly. It cuts off some of the probabilities here, and then it overestimates some of the probabilities on the other side. To correct this though, say we slid this whole thing just like 0.5, right? You can do that, and it increases the accuracy of the calculation. So at least that's one way to look at how it is an error. So what you can do then is take and add the 0.5 to x. So we could use 8.5 for x, because we're looking at less than or equal to. If we're looking at greater than, we also want our value to be a little higher, but we're coming from the other side. So we would be trying to find, for example, the probability of greater than or equal to 8. So 9 or greater of successes. So if we're going this direction, if we add the 0.5, we're actually getting if we subtract the 0.5, we're still moving over, and we're getting the same level of accuracy. What we're basically doing is adding a little bit more area to the red curve to get our answer here. So either way works. This is a pretty good rule. I spent a lot of time in Excel looking at this, and this actually really is pretty good. If you use 0.5, it's more accurate in I think almost every situation I looked at. So we want to take, since x is greater than the average. Actually, we can forget this because this doesn't have to be the case. This isn't really a condition, which I thought it was at first when I looked at it. We know the probability is not 0.5. It's something other than 0.5. So we know it's going to be skewed. So we might want to use this continuity corrector. Okay? So the correction converts x to x plus b in the probability, to find in the probability function, if you want to think of it that way. So how do we find z? Well, to find z, we have to find the first x plus b, which is 8 plus 0.5, and that's 8.5. Then we got to subtract the average. We already know the average is 5, so subtract 5 from that. We get 3.5. Now we're going to find the standard deviation, which we found and I talked about, that's 2.04. So divide that value by 2.04 in this case. We get 1.71. So we get a z value of 1.71, and when we look at a table for the normal distribution, now we can approximate it. So it's positive 1.71, so that's somewhere in here if you look at it. And when you do that, you get, let's see, you get 95.64 over 100. So that's 0.09564 for the probability for the normal approximation. But is that right or not? So let's prove it. So if you take, and I did this in Excel, you get 94, or you get 0.9494 for your value under the binomial exact calculation, which is where you use this formula that I talked about here that's very tedious. When you do that, you get this. So these are not too far apart, and it was probably worth the work if you don't really care about the resolution of stuff. I mean, it's pretty close. It's probably not worth the work to try to figure it out in most cases. And so that is exactly how that's at least a way to approximate the binomial distribution using a normal distribution. I hope you enjoyed this. Thank you.